Hope the audio is okay here. Because it didn't say anything just now, right? Why didn't it say anything? Is it? Yeah, the thing's shut off. Yeah, that's fine. Right. All right. So anyway, that's all set. So yeah, the tour went pretty good. I don't know. What do you think? Pretty cool. Only two people, but this was pretty good. I mean, it was like 3 hours, right? It's like an incredible length of time. I've never been on a tour that's more than like an hour and a half. I think because well, the first guy was trying to rush it through, and I didn't really understand why. But then I realized afterwards why, because it's like crazy. But I thought the first part was the most interesting because all the machines, like all the analytic machines and stuff, I've seen it. Everyone has those. So I mean, it's nice to see them all in one place. It's pretty impressive to see the kind of firepower they have there. And it's right up the road. But um, anyway, it would be a good place to co-op in that part. If that's, I mean, I think. But he said there's jobs, so like in the analytic. So I mean, probably if anyone's looking for jobs in polymer analytics stuff. But I've never heard someone come out and say they need people before, either. So it's kind of interesting. But it's funny, those like the polyolefin companies are a little weird because they'll go through these cycles. So it's a boom and bust commodity market. It's like suddenly there's a huge demand, like the economy picks up, they need a lot more polyethylene. So then like about 3 or 4 or 5 years later, the companies say, oh, geez, we aren't producing enough. Like we can make a lot more money if we built another plant. Then they hire people. And then like everyone does that, all the companies, then there's a flood of polyethylene on the market. And then it's like it busts and they fire everybody. It's just kind of like this cyclic, it's about like a 5 to 8 year cycle. So if you can survive one of the humps, then you're pretty good, But usually, so the new people are the first ones to get lopped off. So it's kind of a funny business to get into. Anyway, I mean, on the other hand, like I know like 4 people that got lopped off that way from there, and they all went off into like one's at International Paper now, one's at Cabasil doing semiconductor manufacturing. So they all and one's in the rubber industry. So it's like basically one retired, but basically they all ended up, the guy that retired's best off. Like he invested in metals, precious metals, and made like a fortune somehow during the cycles. He figured out this cycle thing, I guess. But anyway, so they all end up doing pretty well because especially the analytic, because that's used in all the different industries. So anyway, so this homework, let's see. Let me just go through this thing. So anyway, in the one of the questions, I found something else. Like I've got the paper that was referenced in the DeGen's paper. So he gives that. I mean, I just kind of got that last night. So that's latest on my memory. So get this equation, right? So that equation, if you go back to, so it originates in this DeGen's paper, right? In 1975, I guess, something. So he's got somewhere here, he's got that same equation for the second Gill coefficient. Where is it? It's in this paper somewhere. Short paper, so I shouldn't have a hard time finding it. WT, coefficient of a monomer interaction. I guess he gives it in the text somewhere. I don't exactly see it right now. It's somewhere in here, and it's also in that. Yeah, I don't see it in there. It's also in this Halperin paper. So kind of, so here, it's here, right? So it's the same problem. It's not the right form for second zero coefficient. It should be B minus A over T, right? And it ends up being B and minus T or something, right? So it's not the right form. It's actually the inverse form for temperature that should be. And then they cite, I don't know if it's this guy that cites, it's DeGennes is the one that cites, he cites Flory. So he cites here, he uses one to cite it. So he cites Flory's book, which I looked through that, it's not in it. I mean, as far as I could see, it's not there. It's a 600-page book. So it's got, but then he cites a Stockmeyer paper. So I went and got that paper. I mean, I got it from Interlibrary loan because you can't get the paper that old. And then if you go to that paper, he's just got the normal B minus A over T for the second Viral coefficient from van der Waals. This beta is the second Viral coefficient here. At some point, I gotta explain this thing. So I think it was a matter that the way I see it, DeGennes like wrote down here. So this is the excluded volume, and then minus, and then that times that is A over T. So that's a van der Waals expression for it. Right. So and he calls it beta. The other guy calls it nu or V. And then the other guy calls it something else, right? But it's all the second Viral coefficient. So anyway, so the original Stockmeyer is a guy at Dartmouth in the 50s and 60s up to the 70s. He's a pretty well-known guy. I'm not sure exactly what he did, but he's like one of the fathers of polymer science. So anyway, it says MIT, but he was at Dartmouth. So anyway, so anyway, it looks to me like DeGennes just like put something in this paper, and then everybody just copied it, and didn't ask any questions about it. Oh yeah, here it is right here. That's the DeGennes one, right? And then somewhere here he references one for that. I think it's the beginning of the paragraph. So it looks like he just made this up like off the top of his head, and like it wasn't right. And then people, because the guy won the Nobel Prize, and like they just copied that equation over and over again. It's not the right equation, but yeah. Yeah, well, this is a common, for a critical phenomenon, that's a common expression to talk about the transition temperature, like a unitless transition temperature. So that expression itself is pretty common. But for the second Viral coefficient, it doesn't work. So yeah, you're right. It is a fractional, and that's why it's used that way. Like it's used from the phase transition theory of Landau equations. This is a Landau expression for the critical temperature from something physics. So basically, it doesn't belong here. It's not the right expression for the Viral coefficient. It's the right expression in some cases for something, but not for this. So anyway, it's kind of weird because I went and looked and I thought, well, Stockmeyer's probably got that in there, and he doesn't. He's got the right expression. So DeGennes, I think at one point I looked and he had published something like 650 papers. So the guy was like a paper mill, right? And some of it is like seminal work, and some of it is just not good, like it's mistakes, right? So I think it's a matter of quantity, and some things got out. Also, like when he submitted things, because he was a Nobel laureate, and like he was a pretty high level Nobel laureate. He was really productive. So, and in 3 different fields. It's like liquid crystal, polymers, and superconductors. So he first did superconductors, and he went to liquid crystals. He wrote like seminal books in both those fields, and he wrote a seminal book in polymers too afterwards. Right? So the guy was like, when he walked into a room, it was like, ooh, so anyway, he got away with a lot of stuff because of that, I think. So this is an example of like how you can, and then that gets filtered down, and people, so you can't exactly trust things. All right, so there's that business, and then let's see. think everybody got the first order, second order thing. Expansion. This thing you had to go and I kind of indicated, at least someplace, that there are the two equations, just compare the two. And you can just say like 4 of the terms are the same, and then or 3 of the terms are the same, and Colbeck's has 2 of the terms that are different. At that point, I think you just have to say something about, I mean, you just say they're different. That's probably good enough, you know. But some people gave kind of an explanation for why they're different that was kind of coherent. So I gave extra points if you did that. Then how does it? This is a second drill coefficient thing. And then this Pucell's law, everybody got that. So it's good. Everyone compared it, and a couple of people gave pretty good explanations for the exponential term and they used. And then this thing, I gave an explanation in class, and then I got a lot of different explanations. Some of them were like totally off track, so I took points off. Some of them were like pretty close, you know. So this is kind of open-ended. There isn't really an explanation for why it was like that. He doesn't give an explanation, and basically it's just say what you thought. So I either liked what you said or didn't like it. You know, so it's kind of an opinion thing, I guess. But I mean, unless it was completely wrong, you know. But anyway, so any questions on that thing? That's probably good enough for. All right, so that's what we do every week. We go through a paper, you know. So you'd have to read the paper to understand it.
All right, so a question on these, did they, which source was, I forget the publisher of it, was it like a?
It's in Macromolecules, this paper.
Yeah.
Yeah.
Okay, so they didn't have to like just pay, they got reviewed.
No, that's an ACS. So
Okay.
Chemical Society is the largest, it's the largest science organization on earth or something. And their meeting is the largest meeting of any meeting. They have 2 of them a year. So yeah, ACS is pretty high caliber. It's all centered in Columbus. That's where they publish from. I'm not sure why, but it ended up being probably the cheapest place or something. But
Yeah, I just didn't know too much about like the organizations and whatnot.
yeah, ACS journals are like, there's a lot of them, you know, and they're generally like, so if you just introduce a new journal, if it's an ACS journal, it's automatically like high mid-level. Right. So, and then some of them get to move up, like the JACS, Journal of American Chemical Society. That's the tier 1. That's the top level journal. So it'd be like you publish in Nature Science, then you go to PNAS, the Proceeds National Academy, and JACS, and then PRL, Physical Review Letters. So those are like, there's a few others that are like at the top of the pecking order. And there's some specialized journal. Oh, there's like in medicine is like Cell, you know, in Journal of American Medical Society or something. They go by citation index, and the medical journals always get about 10 times the citations of any other science area. So you have to kind of divide by 10 with medicine, you know. There's more money in it. I guess is what it comes down to. So, but anyway, so and then there's a bunch in the middle, you know, like Polymer, that are kind of mid-level journals, and these pay journals that the kind of the bottom feeding things. Although it's pretty hard to tell because the bottom feeding things, so they try to, so you judge them by their citation index, like you have a paper, how many people cited it. So they can kind of weasel their way to get higher citation index too. Like you publish a lot of reviews, a review is going to get a lot more citations than a paper because it's got everything and all the other papers in it. So you can just cite the review. So there's ways to manipulate the citation number.
Cite the review, they cite all of them. This one she's that.
You aren't supposed to do that, you know. You're supposed to cite the original source, but people don't do that. They're lazy. Yeah. Yeah, it's like saying the Encyclopedia Britannica, you know. It's like, well, yeah, that does cover World War II, you know, but it's not the primary source. No, so, or you could just say Google, you know, and it's like cover everything in the world, I guess. But so yeah, that's how it works. Like that's probably why people publish review articles so that they can get a higher citation. Like the person has a citation number too. So Anyway, it's a game. So, you know, all right.
The goal of doing this like explaining 103 changes. Things in your
It changes. The goal is to say like it changes, right? So one's higher. There's a weird thing happens and he doesn't note it, right? So he's got the free chains and the tethered. So the free chains are yellow, right? That's just, you just take the stuff, put in solution, hold it in your hand and it turns white. What temperature did that happen? And the red one are the tethered. It's like when you get small tethered ones, and it's on heating that your phase separating. So they phase separate earlier, so they're less miscible when they're tethered. Okay, so I said that's because they're probably heterogeneously nucleating on the surface, like they can fold over and pile up on the surface. And that's what I thought. They're all, I mean, I don't know what else is different about them. They have less translational entropy, that's for sure. So there's a difference in the entropy could drive it, I guess. And entropy drives mixing, so you could say something like that. But then when you get to high molecular weight, then the ones in solution phase separate first, and yeah.
As larger, there's more laser, longer, and kind of can tangle it more with other polymers.
Mhm.
And the ones that are free can kind of angle it like going or like less interaction with solving. And the ones that are better and can't tangle it as much.
You got to be careful. So tangle, you can only measure tangle with a dynamic measurement. Okay, so you can only like, is it entangled or not? You can't do it in a DSC. You can't tell it, right? Well, kinetics isn't going to change the thermodynamics. That's what I'm saying. So this tangle thing is a kinetic feature. Doesn't have to do with miscibility. I mean, it had to do with kinetics of phase separation. I mean, so it changes the speed of it. But the speed isn't what's being, this is supposed to be an equilibrium measurement. So it's that you have as much time as you want. It's like a no time limit exam type thing. Yeah. It's basically, you can't use an argument like tangles. That isn't going to work. You have to keep in your mind somehow, and it's easy to slip between one and the other, especially when you're measuring like intrinsic viscosity to get the overlap concentration. That's a kinetic measurement they use to get structure. So people cross the line all the time. But basically, you have to be careful not to do that when you make an argument, because you have to keep it clear that when you're measuring an equilibrium thermodynamics or you're measuring kinetics. So, and then they both have the same concentration, I guess. So, I mean, like your argument, so the concentration of the two is the same. They're both dilute. So there's not a difference in concentration. So that's the other thing, like you're getting, I mean, it's logical what you're saying, but you've gone down like a rabbit hole, like a red herring thing. So it's not concentration because they're at the same concentration. So when you start arguing entanglement and concentration, you've already made like two things that are like, yeah, crossing the double yellow line. You know, so anyway, I can, but it's easy to, I can see why you did that. And I mean, and it's good that you did it, but basically you got to understand that it's a mistake. You know, and it's a hard mistake. Like you can't fix that mistake. You know what I mean? So basically, even though people try to weasel around it, right? So, but basically, if you do, you're gonna have to make a long argument about why kinetics matters to thermodynamics when they're defined to be different from each other. And so anyway, anyway, what I said was that when they're tethered to the surface and they start to impinge on each other, and somehow that makes them more miscible. I mean, they squeeze into that rod-shaped thing, so somehow they become pillars. So I don't know. That isn't really convincing either, but it's kind of the same thing you're saying, you know. So, but the way you said it though wasn't right, and the way I said it is right. So, because at least in my mind. So yeah. So anyway, it's puzzling they didn't mention that the things cross, you know. So something happens as a magic molecular weight, which is around, basically 100 is around the entanglement molecular weight. So it is near the entanglement molecular weight.
Part of it.
Mhm. Yeah, it's right at the same number. It's where the chains start to fold. Where they start to bend over. So anyway, did I answer what you asked?
Yeah, I got
Yeah. Okay. All right. So is that okay then? Yeah. All right. So let's see. Yeah, I wanted to get the to go back here. I wanted to get these slides. I changed them by one thing. So let's see. So went through all that. All right. So I wanted to. So basically, the way that this concentration blob I mentioned last time. So so when you have so when you have the chains start to overlap at the C star, and then after that point, at sizes larger than a certain size, like C star for some. So C star depends on the molecular weight. So there's some molecular weight. So you have a fixed concentration, and you have a high molecular weight. So there's going to be some molecular weight where your effective concentration within a coil matches. No, your molecular weight has a concentration C star. You have an experimental concentration that's higher. So you're over the overlap concentration. So they're overlap. But as you get to smaller segments of that chain, well, they're below overlap concentration. Like you can calculate their C star. So say N is 2, it's going to have a really large C star. So your concentration for a 2-unit chain is going to be expanded coil. It's not going to be theta coil. So when you get above C star, it becomes Gaussian. Below it, it's expanded. So basically, there's going to be a cutoff size scale, this scaling size. You can get by saying that scaling size doesn't depend on molecular weight. And the other thing is that when it's a random coil, you don't get scattering contrast from it. You just get the scattering contrast you get from it is just the fluctuation. So that's in here somewhere, right? I cannot find that usually. There's a picture of that. I think it's in this or it's in the other one. Anyway, I showed that last time, but so basically, let me just do it here. There's a graph of that. So you do log of the scatter. So you're going to shoot a beam at the stuff. So say it's water, right? And then it's going to pick up the intensity at some angle, and Q is 4 pi over lambda, the wavelength, and sine at that angle, at 2. And so if you plot log of I versus log of Q, and I goes with the number of things times their kind of electron density squared. There it's binary. You have 2 things interfering. All right, so if you have just water, and it's just flat, because the water's got these fluctuations, like you say the average density versus kind of position or time. So you're fluctuating all the time, right? In other words, because of KT is driving these fluctuations. And then when it goes up, you get more crowded kind of water molecules, and they want to disperse, right? So that's like a pressure, that's osmotic pressure driving the things that get clustered to be more dispersed. And when they get really dispersed, they want to bounce back and get to the average concentration. Right? So it's kind of bouncing back and forth, and KT is driving this fluctuation over time. So each of these little clusters has a number of electrons, say it's X-ray scattering. So you have a number of electrons squared and a number of those blob things squared. Right. So that's what gives you a contrast. When you shoot a beam of light through water, you get some scattering. Right? And it's going to be just a flat scattering number because the KT is driving it up. So that thing's going to be related to 1 over the second zero coefficient. So it's going to be like KT over whatever we had the KT over A, basically. Right? So like the over chi or something. Right? So basically that'll give you, you can measure like what's the osmotic pressure of water that way, if you want. But so anyway, when you have the Gaussian chains and they're overlapped, right? So this is like a fleece material, like you have randomly arranged fibers. And if you look at it on a large scale, well, it's just a sheet. It's just a sheet that's got contrast, right? Like a fleece, like this thing. If you look at it from far away, yeah, it's a solid object, right? But it's got some kind of scattering to it that'll just be flat that's related to this compressibility of it, this osmotic pressure. If you zoom in, then you'll be able to see the fibers, right? So that cutoff point, so you'll have like flat like water. And then when you reach that some kind of point, this concentration blob size, then you'll see like the -5/3 dependence. You know, it's I, it's like mass. Q is like 1 over size. So you end up with mass goes with size to the dimension of it. Right. So you're gonna get this -5/3 would be like the dimension, 1 over the dimension. But it's going to be the negative of the dimension of the material, like the 5/3 expanded coil dimension. And then you get this blob size here. If you dilute it down and that thing goes up more, and finally you reach the full like coil size, which would be like the radius of gyration of it. So this would be like 2 pi over the radius of gyration for that here. But as you increase concentration, if it's intensity divided by concentration, then this thing will just keep marching down as you increase concentration. You can measure that blob size from it. So for that reason, it's like invisible. Like once you get to this size, the overlap, then you can't see anything just like the fleece. You just see a piece of fabric that's constant. It doesn't matter what size scale you look at the fleece, it's a fleece. But you zoom in, when you zoom in, then you can start to see the chains. So basically, if you do a measurement at this size scale, that can't depend on the molecular weight of the fibers because you can't see them, right? There's no dependence on molecular weight of the fibers at that point. Right? So anything above the overlap concentration, there's no end dependence. Right? That's kind of rule 1 of the above the concentration thing, right? So, I mean, the way to get around that, so if you could take like a small percentage, like 1% of the chains, and then deuterate them, so that paints them red for neutrons, right? And then put that chain into like a 50% mixture, then you'll see the structure of that chain in a 50% mixture. And so you have like the fleece, then you'll have like some red fibers in it. You can measure those red fibers. And if this deuteration doesn't do anything to the interactions, you can say like I can see a single chain. In that case, you'll see this transition, like it'll go -2 and it'll go like -5/3. You'll see the transition, you can see this blob size there. Right. So differences with no contrast, with no deuteration, you see nothing. You just see this blob size. With deuteration, you see 2 regimes. Right. So it's possible to see both. Anyway, so that's how you get this blob size goes with a C by C star. You say that this thing's you're gonna do a reduced concentration, reduced by the overlap concentration. It's going to be to some power P. When this thing reaches the overlap concentration, it's going to have the size of a expanded coil chain. And you can say expanded coil chain is 3/5, end of the 3/5. And then this, yeah. Oh, sorry. Oops. I didn't hit the project button here. Yeah. All right. So first you have C stars n to the -4/5, just by saying n divided by r cubed. R is n to the 3/5, cubed is 9/5. 9/5 minus 1 is 4/5. So you get the 4/5 from that C star. Then you say, well, everything above C star, it's going to be normalized by this. Just say that. And it's going to be a power law. Just say that. So it's like 2 kind of just say that's here. So you have C by C star by P. And then the coil size when you reach C star is n to the 3/5. You have 3/5 here. Then this thing would be P times 4/5. So 4P by 5. So that number, since this thing can't depend on molecular weight above the overlap concentration, and that you can solve for P, it ends up being 3/4. you can just go back to this equation and plug it in, you have the 3/4 the blob size. Right, so where that was first used. So where that was first used was with the osmotic pressure. So where that is here. So like yeah. So osmotic pressure, I said before, you have two chambers, like it's as if this was a vacuum and this is with a gas. But what this really is this has polymer in it. It's like polystyrene and toluene. This is just toluene, right? So when the two are cooked together with a membrane that allows toluene to go through, but not polystyrene, then the toluene wants to dilute the polystyrene, so it raises the pressure here. Right, it wants to go to the right, and the polystyrene wants to go to the left, but it can't because there's a fence there. Can't get through. Right, so basically you get this pressure difference, and that pressure difference is the osmotic pressure of the polystyrene and toluene. Right, I mean, if you change the solvent, it's a different number. Right, because this thing's going to be through an expansion. That's going to be the second Vierel coefficient. Right, the first is this thing's going to depend on the concentration. So rho's the concentration here, and then it's a concentration. So this is called a colligative measurement, meaning it's a counting measurement. It doesn't matter how large those things are or how small they are, right? It's just how many there are, right? So boiling point suppression, there's various things that just depend on how many things you have, right? So that means if you're going to use this to measure molecular weight, then you get the number average because you're counting how many. It's a counting technique, right? So n is going to be the number average molecular weight. Compared to light scattering is going to give the weight average. Right? So number average is the mean. That's just like what you call the mean molecular weight. Anyway, so that if you do an analogy between gas pressure and this kind of osmotic pressure, right, then you end up with the same Vierel expansion, and you have the first Vierel coefficient would be for a polymer is going to be 1/n, the molecular weight, right? And then so that's a useful thing to measure the molecular weight. Like it's kind of easy to do, right? And then it also gives a different moment. Like usually the lower order moment, the better. So the number average is the second moment. It's like or it's the first moment. It's a mean, right? And then the weight average is the second moment, I guess, second to first ratio, right? So anyway, so we can get this Vierel coefficient here, and then Flory worked out that this B2 from this is going to be 1/2 minus chi by doing a little business with his Flory-Huggins theory. Right? So I wanted to kind of go through that. There's a little bit of nomenclature thing here. So you have in the light scattering measurement. So if you're doing that measurement, you don't exactly know what it is you're measuring, right? So you don't know offhand, you don't know its molecular weight. So let me go back to that. So if you have this log I versus log Q, and you have this kind of thing, -5/3, right? So you can get this thing, and you know that thing is n squared. Like how many coils are there, and then within a coil, like how many electrons, like the number of electrons per volume, right? Squared, because it's binary. It's like interference between two of these, but so you have two, so you have this number has to be squared, and if you increase the concentration, intensity is proportional to this. It's proportional to the number, like how many you put in. And so anyway, so that, let me see, what was I talking about? Polymer, yeah, good. What contact? It has something to do with this. Let's see. Two. Yeah, let me skip that. Sorry, I lost track. So we have this. I want to go through this math thing. Oh, it's this slide. Oh yeah. Okay, that's what I wanted to say. Sorry. So this is going to go to like 1 here somewhere for the rod part, and this is going to be like the Kuhn length or the persistence length. And so basically, if you know that number, that intercept, right, and then you know this intercept. So the number of these and that is the ratio of those two numbers. Okay, so like this intercept and that intercept, call it like G2 over G1. plus one, because when that goes down to the bottom, that's going to be one of them, right? And then if you had two, it would be two times that. It's going to be relative to this. That would give you actually the molecular weight, like the weight average molecular weight. I'll show you why it's weight average later on, but anyway, so, but if you don't have this part, so say you don't have that, then you don't have you can't get the actual molecular weight of the thing. So you can't get actually the B2 without knowing what the thing is that you're measuring. So because of that, if you just have this intercept, that I naught, and that's going to be proportional to 1 over A2, not B2. And A2 divided by the molecular weight squared is B2. And B2 is the thing that's the excluded volume. So the thing you measure is in really weird units. Excluded volume per mole, it's going to be in like centimeters cubed per mole per gram squared, and then grams per mole. Let's see, grams squared per mole squared. So it'll be like centimeter cubed mole per gram squared. So you see this A2 plotted, and you're like, what's the excluded volume? Which is something you can put like you can calculate the excluded volume from a model. You can't not calculate A2 from a model. It's because you don't know what the thing is that you're looking at, right? So yeah.
Is that also correlate with the like part C of
Yeah, it's in the papers. It's in those papers.
okay.
Yeah, it's in the papers. You'll see like they'll give here's the value of A2, and they'll give units of centimeter cube mole per gram squared. Then you're like, what is that? I know centimeter cube, like that's a volume. And I can calculate a volume. I can draw a picture of the thing, get the volume. But A2, so if you see A2, the only thing you can say about it, if A2 equals 0, you're at the critical point. If A2 is positive, it's miscible. And if A2 is negative, it's immiscible. But anything else is anything, because it's A2 divided by the molecular weight squared that you don't know the molecular weight squared. Right? So other than comparing two things, it's a useless number. And for the 0 point, like if you can extrapolate it linearly, well, you should go with 1 over t. So if you plot A2 versus 1 over t, and then find that, you can find the critical point if you have 2 points. So it's useful in that sense, but the actual value is meaningless unless you have the molecular weight, right? So it's kind of, and that's not, nobody says that to you. Like nobody will come out and say like, what is this number that you're looking at? Like they'll report the second viral, it's confusing enough as it is. Then they give units of centimeter cube mole per gram squared. And it's like, well, what is that? Like here, I think he's given units here, and all these things are in units. Oh, all these things are in units of that unit, that weird unit. So you can see I scribbled down to try to figure out what he was talking about. Ended up with, oh, that's the thing I want, and I got to divide by the molecular squared, which you don't know. So I mean, you can get it from a light scattering measurement. Basically, if you just have the viral coefficient, you can't get it. You need that somehow to get that. So normally people don't measure the persistence length. They normally what they normally do a calculation of what the persistence, like they say they have a chemical unit or something, and they know the whatever of that, and they can divide by that. So do a calculation to get the B2. They don't do the measurement of it. Yeah, if you don't say you just did the measurement, like, all right, so in that case, you need to get the intensity in absolute units too. So it's more complicated measurement to do. So anyway, that said, so yeah.
That variable G.
G's the shear modulus here. G is just the cross, it's just a number. I mean, it's just the intensity. G's the shear modulus. Yes, that's a dynamic measurement. This is static. Yeah.
In this case,
G's the intercept, the I naught. Yeah, just the I naught. Yeah, it's just the I naught. There is a G that next week we'll talk about G. G prime, G double prime. Right. That's the storage modulus. I don't know why it's called G. This is called G because it's Gunnier's law. Why is the storage modulus called G?
Boltzmann probably called it G in his initial theory.
Good. All right. Boltzmann did it. All right. It could stand. I mean, the Gibbs free energy is because it's Gibbs. Helmholtz, they call A or F. I guess H was already taken for enthalpy. So I don't know. You got it. One thing is you got it, like you can see from this virial coefficient, one guy calls it nu V or W, and the other guy calls it beta, then B and A. So you got to get used to like people can just make up whatever symbol they want. And then it just to make things more confusing. Or there's a certain little school of people that used, like say the Kuhn length, and they'll use A, sometimes they'll use B, sometimes they use L, sometimes they use LK. I mean, sometimes it's P, right? So you got to get used to like, oh, there's that symbol, what is it? And you go convert it to whatever symbol you like. Like viscosity symbols, like mu, eta, some other nu sometimes. I said nu. There's some other symbols they use for viscosity. So you got to somehow get over that the symbols are switching all the time. But it's good. Like what you said is good. Like you have to say like, what is that thing? Yeah. Yeah. I mean, a couple things don't change. Like capital T is temperature and small t is time. So don't use small t for capital T. And that's kind of it, So most of the time P is pressure. I mean, so but then there's these other things that are P, but so anyway, so we got this expression, right? So all right, so Flory-Huggins equation, right? So we got entropy of mixing. So this is the same as mixing marbles thing. Like you have ln of the concentration, except he's using volume fraction instead of mole fraction, right? And then if it's a polymer mixing, you divide by n because you're talking about the things that are mixing are polymer chains, not mer units, right? So you talk about the divide by n here, right? And then if you want to add in like a Hildebrandt term, you put in this chi parameter. So this is all written. So chi is per monomer unit per kT. So chi is has a temperature dependence, right? So there's no temperature dependence here, but so this is a free energy of mixing per mer unit per kT. This is from Flory's book, so basically you got to get used to small f is a free energy of mixing of a mer unit per kT. It's not the free energy of mixing, and it's the Helmholtz free energy. So the Helmholtz is if you have a constant volume, like you do a computer simulation, you have a grid, you're going to mix things, and then the volume doesn't change, but the pressure can change. So if you want to know the Gibbs free energy, you want to equilibrate two phases, then the chemical potential is equal, and that's the derivative of the Gibbs free energy, not the Helmholtz free energy. So you convert by adding PV. So you have to take this guy, which is the Flory-Huggins equation, multiply by KT, multiply by the molecular weight N, right? So you get a chain instead of one unit, and then add in PV as a system to get the Gibbs free energy. Right? Say you have like the polymer in solution and just the solvent, and you want to say that across that membrane that the chemical potential of the solvent on the right is the same as the chemical potential of the solvent on the left. And then you want to say that the chemical potential of the polymer on the right is the same as the chemical potential. There's no polymer on the left. So you just do the solvent, right? So you do the chemical potential of the solvent on the right is the same as chemical potential of the solvent on the left. And then you're going to say, and I'm going to add in a PV, and that's where I get the osmotic pressure from this thing, because I add in the PV term, then I have a P, then I can solve for P, which is the osmotic pressure. Right, so that's the whole theme of this thing. So, right, so that's kind of the picture. You want to get that P, and you're going to get it from the Flory-Huggins equation, right? So, let's see. So anyway, so we got. So this is called the thermodynamic square. That's how you can figure out all the equations. So like, G is A and then VP, and all of those work that way. Like, so basically H is G TS plus TS. Like, so it's a way to remember all the equations. Anyway, you can remember actually every thermodynamic equation if you remember that square. But so G A VP, if it goes the other way, like AG, and then it's minus PV, right? So the Helmholtz free energy A, which is also called capital F here, and the Gibbs free energy are related by adding in PV to it. Right? So you have that at the last end of this thing, PV. And then what you want to do is take the derivative of capital F, which is small f times KT times N, right? And then you want to take it with respect to changing the number of solvents. So chemical potential is a change in the free energy when you pull one solvent molecule out. One, right? So it's just like removing one of the two system. The system has omega things in it. So N solvents, N polymer, and then each polymer counts as N. So N times NP plus NS gives you this omega, which is a total, like if you have a grid, how many voxels are on the grid, right? So right, that's kind of the picture. So it means that if you want to talk about changing the free energy, the Gibbs free energy by pulling out one solvent molecule, they have the chemical potential of the solvent, holding the number of polymer constant, temperature and pressure. That means this thing changes by one. So you have that capital DF derivative with respect to omega. Omega is going to change by one because NS changes by one. And the change in omega with respect to NS, right? And that means that's going to be just one because this term drops out and that is one. And then you need the change with the composition change with NS. So these things all pile up into a bunch of algebra. And then plus the PV, where you're going to get the osmotic pressure from that. Right. So anyway, so you can solve all those things. And then you can write an expression based on the original small f, this Flory-Huggins equation, this guy, the free energy of mixing, the Helmholtz free energy of mixing. You'll end up with this expression if you plug all those in, and then plus this PV, which is going to give you the osmotic pressure. Then you say this on the one side, the composition of polymer is 0, on the other side, the composition of polymer is some polymer. So you take the difference between no polymer and polymer, and then you'll get this kind of term, right, from that. And then basically, so you set the equilibrium between the two parts, except one side has osmotic pressure with it, and the other just has pressure. The pressure drops out of the thing, and you'll just get what the osmotic pressure is. It'll be like this derivatives of these. Then you plug in the Flory-Huggins into this. It's a little bit involved. This is in Flory's second book. There's a chapter on osmotic pressure. Just kind of the theme of that chapter, right? So he ends up with that if you do that all the way down, and you have to do this little ditty to get rid of the log of 1 minus phi, because exponential of x is 1 plus x squared by 2. So log of 1 minus becomes, you can work out from that this expression. And this expression, because it has a phi in it, it kills off a phi in the final expression. And you have phi squared by 2 is the first of the power series expansion. That's where you get the 1/2 from. So it ends up being like, because there's also a chi times phi squared coming out of this. So end up 1/2 minus chi is the term, and the lead term is phi by n. And then the osmotic pressure is just that thing, right? Which would say that if you plot it, so you should get that the osmotic pressure is a function of concentration. So you divide it, because the lead term is concentration, so you take that out. So you take pi by concentration, and then you have KT, so you divide by that. So osmotic pressure times molecular weight, divided by KT, divided by concentration, that should be a constant, right? Until you get to the higher, the first term would be a constant, right? If you just show it against molecular weight, you have this series that change. But if you divide by molecular weight, then they fall on top of each other. If you have the concentration divided by C star, each of the molecular weights has a different C star, right? It's a minus 4/5 power of the molecular weight. So right, then you can get a universal behavior if you plot pi versus C by C star, right? And then, but it isn't a power 2 in concentration. Out here, it's this weird 9/4 power, right? This work was done in Cincinnati at Procter & Gamble by Sal Noda. This business about figuring out the business of how the osmotic pressure changes. So it's kind of interesting to mention it. But anyway, so you can get that 9/4 pretty easily. You can get it by saying the osmotic pressure is going to depend on 1/n. It's going to be KT, because you already know that, because that's how this works. You can normalize the curves that way. They say it just generically depends on some power of this reduced concentration. And then you know that C star has this independence. Then you can write, and you know that the pi above the overlap can't have an independence. So you do the same trick. You solve for the P by saying that that thing can't depend, so it has to be a zero power on molecular weight, and you can get this 9-force dependence on that. Right, and that depends on the concentration blob model. But yeah.
Yeah, that's the thing I was about to ask, but the concentration over, where it's on the axis is concentration and.
By C star, by what?
Yeah, I was wondering what the axis was.
This is C by C star. So this thing in the brackets, right? And then this is pi. And then you get rid of the molecular weight dependence. So pi m, and then divided by KT or RT. I mean, per mole would be RT. Then divide by the concentration. So pi m by C RT. So it's just, that should just be a flat number if you're at the low end. If you're at the low concentration end, only the first term counts, and you removed all those, that should be like 1. That should just be a constant number. Actually, 10 to the 0 is 1, so it should go to 1. He's taken everything from here, piled it into the left. So the first term is 1. The second term should be, because you've taken out one concentration, should be just linear in concentration, which doesn't work. And then if you do this blob model, you get this should be 9/4. It's 1/4 more than linear. And that's the way it acts. That predicts the actual number, you know. So this blob model, this was like the demonstration that the blob model works. And then also you can do a neutron scattering measure and actually see the thing. They can measure it. It's basically, it actually does that, at least statistically. Again, the chains are always like moving around all the time. So it's a moving target. So taking a micrograph of this isn't going to work. You know, so you can only measure it with scattering or do this. Osmotic pressure is also averaging a whole system. So it's a concept like a cartoon you could never see in the real life, but it's a cartoon that can predict the behavior. And it's kind of a simple model, like you can put your handle on it, make some predictions with it, things like that. So anyway, that's kind of what we have time for here today. But so yeah, so I'll do some paper on this stuff, find something on this for Friday.
And that square, how do you use that square?
There's a lot. I got a whole thing. I can send it to you. You know, it's really useful. Like all, you know how there's so many. All right, so all the Maxwell equations you can get from this by saying ds dp. Let's see, this thing. What is it? ds dp equals dv dt or something. So you can get all the Maxwell equations out of this. You can get all those basic equations. You can get all the derivative equations. So there's 3 sets of equations. And you end up this like 40 equations you can get from that square.
Yeah.
But they're all different rules. Like the Maxwell's are like a U, like a horseshoe thing. These things like go there, there, and across. And then the derivative ones, I mean, the cross terms are always like the energy, right? So you have energy, 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 and then PV and ST. So I can send you a thing that you can just Google it too, you know. It's called the thermodynamic square. But they should in every class at the first point, because once you have that, then when you see the equation, you go back and check it and you're like, oh yeah, that's right. Yeah. Yeah. Yeah, I think it's pretty much invaluable because you get so buried in stuff and you won't know where the mistakes are in something. And you can just, I mean, you can calculate all those equations. It's going to take you a long time. And you can remember some of them, like G is delta G is delta H minus T delta S. You know, but anyway, even that you might not know. Like, so you have G H minus ST, like is in it, right? Delta G is delta H minus delta S T, right? That's like the standard Gibbs free energy thing. But so anyway, all right. See you guys. Right.
What are the topics you want to cover?
I'm gonna have to go through. Like list them for you. Yeah.
Okay.
I haven't done it yet,
That's
but
fine.
yeah.
You
So
can just let me know before Monday.
yeah,
Then
I'll just have a list of like 1, 2, 3, 4, and if you need to fill in more for it, you know, that's fine. But
Do you want me to make slides or do you want me to use your slides?
I don't really have any slides on it. You can just use this thing if you want.
I'll make slides.
If you want to make slides, it's fine.
It's easier for me to make.
I think you can just go off the top of your head. If you miss stuff, it doesn't matter. If it's wrong, it doesn't matter.
You
So,
just let me know the topics you want me to cover,
yeah,
then I'll just do that.
okay.
Is there any specific